Gobi downhill, problem number 2, mountain bike physics. We watched previously in the video of our extreme mountain biker riding this 2,000 foot vertical drop. We also tracked in our previous story problem his path, so let's do that again. Let's go ahead and pick a reasonable color. Alright, again we'll use this neon green. Our rider took this path through that little funnel there on that ridge, cut back to the left, and then traverse this ridge like so, cut across this ridge, and then again cut across the final ridge to find himself right about there. And that was a roughly 4,000 foot distance traveled, so that converts to 1,220 meters. We also noted in the previous problem that vertical displacement was 610 meters. So both of those measurements are going to be important in our second problem here, which we're going to solve in 3 parts. We're going to treat this as it's a bike ride down a right triangle. So let's change screens and let's look at this. Here's our bicycle. We know our, let me change colors again. We know our bicycle is going to be accelerating down that path, so we know it has both an x and a y coordinate. It's basically going to be, because it's a frictionless problem, a free fall at some angle other than 0, and we know that gravity is going to be working in that direction, friction is going to be working in this direction, normal force perpendicular to our path traveled. We could look at that as a free body diagram, but right now let's just do this. We know that this side of a right triangle is 610 meters. We know that the hypotenuse is 1,220 meters. We need to know this angle for us to be able to determine slope per se. And we know from trigonometry that if we want to find that angle, we can do so by using this equation. The sine of theta is going to be equal to opposite over hypotenuse. So that's going to be 610 meters divided by 1,220 meters. And to get theta by itself, it's going to be inverse sine of 610 over 1,220. And we know that that's 0.50. And doing the calculation on that, the inverse sine of 610 divided by 1,220, we get our angle at 30 degrees. So we know that this angle down here is 30-degree angle. It's a pretty significant angle. And that solves part 1 of our problem. We're going to now use this angle in our second calculation, and our second calculation is going to be a calculation for acceleration. So we know that acceleration is a function of acceleration due to gravity times sine of theta, which is going to be equal to 9.8 meters per second squared times the sine of 30 degrees. That's going to be equal to, and again I'm going to omit units right now to speed things up. It's going to be equal to 9.8, and the sine of 30 degrees is 0.0, which gets us an answer of 4.9 meters per second squared for our acceleration. And part 2 of our problem was done. And if we know acceleration, we can then plug that acceleration into this equation. Velocity squared is 2 times acceleration times distance traveled. And that means velocity squared is going to be equal to 2 times 4.9 meters per second squared times 1,220 meters. And if we want to get rid of that unit, that square exponent there, we know we have to take the square root of both sides. So if we do so, the square root of 2 times 4.9 times 1220 gets us to a velocity which equals 109 meters per second, which is the same exact velocity that we calculated in problem number 1. So if friction is not involved in this problem, slope plays no significant role in how fast this rider travels down the hill. Now, that said, let's go ahead and we know that 240 miles per hour is an unreasonable speed. So let's go ahead and take a look at what his real speed is. If you noted on the video, first of all, he traveled a total of 1,220 meters, and if you clicked off the time on the YouTube video, you found that he did so in 74 seconds. So can you calculate his velocity in meters per second, and then can you convert that to miles per hour? And when you do so, I'm guessing that you'll find that to be a much more reasonable speed, and you'll be able to note the significant impact that friction has on the velocity of this rider. Keep in mind that the downhill land record of 172 kilometers per hour or 105 miles per hour was set on the side of a Nicaraguan volcano in 2002 with an angle roughly of 45 degrees. And again, that record was only 105 miles per hour, nowhere near our calculated value of 240 miles per hour.